Welcome back to class 11. We're going to do an example out of the book using the tables and whatnot to try to get the enthalpy for 1 kilogram of oxygen heated from 300 to 1500 Kelvin. And we're going to assume ideal gas behavior. So let's go to it. And we're going to do a couple different ways, if I recall correctly from what I have written down on this piece of paper here. So the first thing that we're going to do, let's just go ahead and just look it up. All right, so here's our method number 1. Look it up. And so we'll go to table A.8 for oxygen. And at T is equal to 300 degrees Kelvin. And they did do it for Kelvin, didn't they? All right, so we can go to table A8. Boom. And find for oxygen. And find for 300. And here's our enthalpy. So 273.15. I'll put it up here on top of that. Okay. So H is 273.15 kilojoules per kilogram. And then at T is equal to 1500, we could get H is equal to, boom, and right there. Is it this one or that one? I think it's this one. Yep, that one. Right there. 1,540.23. 1,540.23 kilojoules per kilogram. So we can get the change in enthalpies. It can be M times H2 minus H1. Or this is 1 kilogram. So we're going to go 1,545.23 minus 273.15. And we get, I'll put it right down here, change in H is 1,267 kilojoules. And we're going to use that as sort of the control, right? Because there's a reference that we have that tells us this is what these values are. The others we can consider them to be estimating, right? So they're going to be in estimations or an approximation. So in the next one, we're going to look up what the specific heat is going to be at constant pressure. So this is table A5. So we're going to use, it's going to go C sub P for an ideal gas. For as all I know, this is also an ideal gas approximation. But I'm going to assume that somebody has actually done experiments and found this out. So we look up at table A5. Should be pretty familiar with that table. We've been looking up the gas constant often with that. And this is going to be oxygen, right? So down here, oxygen. And let's see what column should we be looking for. So we should be looking for this column right here. And we get 0.922 with the units of kilogram, kilojoules, degree Kelvin. So let's write that down. Write that down. I'm going to start singing everything. Think so? I don't know, maybe. Kilojoules per kilogram, degree Kelvin. And so when we want a capital H, all we do is go mass times C sub P times delta T. Get used to that formula. You'll see it often. 1 times, and we're going to go become unit cowboys here, and just say, okay, we'll stick with kilojoules, and we're dealing with a delta T here. So we just go 1500 minus 300, not write any of the units down. And so now we're going to predict that it's going to be 1106.4 kilojoules. And if we do a comparison, that is that we use this as the baseline and we subtract this from that and then divide by this, we're going to find out that we're 12.68% less. You can see that that's less than that right there, but that's an important thing to note and kind of say, oh boy, that's a pretty big difference, right? So this using a constant specific heat is not necessarily a great approximation, but it's a necessary approximation quite a lot of times for certain things. So it's just recognize when sometimes we do something called an air standard cycle when we're taking a look at like engines that operate on air, which would be gas turbines and internal combustion engines, and we do stuff on an air standard cycle, but it's an approximation because it's just kind of difficult to keep track of the changing specific heats. Anyway, back to the ball game. Now let's try to get this is an approximation. Let's try to get a better approximation for this. And we really have two choices. I'm going to do both choices. So let's go to for an ideal gas from this table. And now let's use table A6. So using table A6 right here we have this equation, and we're going to do it for oxygen. So down here. So here are our coefficients. Let's see if we get them all together on the same thing. For CO, C1, C2, and C3. So I'm going to write these down. So you have 0.88, negative 0.0001, positive 0.54, and negative 0.33. So I'm going to write down that. Am I going to write down that equation? Sure. I'll write down this equation. CP, and this is CPO if you wanted to, based on zero pressure. CO plus C1 theta plus C2 theta squared plus C3 theta cubed. And for oxygen, we had CO was equal to 0.88. C1 was equal to, where'd you go, C1? Negative 0.0001. It's easy to get that number of zeros wrong when there's that many. And then C2 is 0.54, and C3 is negative 0.33. So what we'll do is we have to take our temperatures and divide them by 1,000, and that's what theta is going to be. So let's take about a CP. So this is at T equals, what are we going to do first? 300 degrees Kelvin. We will write out CO 0.88 plus negative 0.001 times our 300 divided by 1,000 plus C2 0.54 times 300 divided by 1,000 squared, and then plus negative 0.33 300 divided by 1,000 cubed, and we get a CPO of 0.9197, right? Kilojoules per kilogram degree Kelvin. Compare that to what we had up here, right? So it's less. So that would be less now. Then we do the same thing for 1,500 degrees Kelvin. Maybe we should put the little zeros in there. I guess they don't have a comma in there. Anyway, you can zoom through this. Oops, I left out a zero in there, didn't I? But I didn't in my calculations. I put them in there. I showed them in I swear I did. There you go. All three. It's easy to mess that up. So we go 1,500, or actually we could just go 1.5, couldn't we? Sure, we could do that. Or we could just be persistent and write it out every time like that, because we're just sometimes stubborn. Just a little stubborn, but just in the right amount. We talk about the happy trees. All right, so CPO for this one is 0.9811 kilojoules per kilogram degree Kelvin. That looks like a little bit like a kilogram. And compare it back up to here. Yeah, it's a little bit more. Actually, significantly more there than it was than that one is less. So now let's have our delta H be M times CP, let's call it 2 T2 minus CP1 T1, or 1 kilogram times 0.9811 times 1500 minus 0.9197 times 300. And what do we get for delta H? We get 1195.7 kilojoules, which is 5.62% less. Huh. Interesting. Let's try one more thing. Let's now alternatively use the average temperature, right? So let's here, I'm just going to call this the alt. Use TAVG for C sub P. So the average temperature is going to be 300 plus 1500. I think we could do this in our heads, but we're going to write it down anyway. 900 degrees Kelvin. So what we'll find here is we will get a CP is equal to 0.88. And I guess I'm going to go to this movie thing to get rid of that. There you go. It does give me this thing right here, but at least I don't get those little squares coming everywhere. They're kind of annoying to me. Got this guy going on. Now we're going to go 900, not 9,000. Let's go now. We could just go 0.9, couldn't we? We could, maybe, but I'm not gonna. Oh, I did it again. Might as well use 0.9, right? Go figure. Well, somebody might be confused by that because they might have like jumped ahead and not listened to what that theta was supposed to be divided by 1,000. So they're going to try to figure out why I was using 0.9 instead of 900. I don't know. I'm just rationalizing. So anyway, we put that in there, and so we can find our delta H is going to be MCP delta T. And so we go 1 kilogram, but this time, I didn't tell you what the answer was. Dummy. 1.0767. This was kind of an interesting outcome. Not what I anticipated. I thought there was a trend. I thought it would be somewhere in between these two, but it's not. It's actually higher than that. So that's kind of a, ooh, wow. Don't just, I don't know. Don't assume, maybe. You always think things as being linear. Don't assume things are linear. It's obviously not linear. It goes there, and then goes back down to there, apparently. All right, so and then the temperature is going to be 1500 minus 300. And then interestingly, it gives us 1292.1 kilojoules, which is darn close to what we had up here. In fact, we're just a little bit over. We're like 1.98% more. So Whereas I wouldn't say that our conclusion is that we never do this, because we do this quite often. It depends on the substance. Oxygen doesn't seem to be a very good one to just be using what you can think of as the ideal gas type of approach, because this is where we get this value at the same place where we get R, right? And remember that the relationship between Cp and Cv is one minus the other is going to be equal to R. So that this is a close relative of R. Here we try to get maybe some more empirical relationships between there to estimate it. And here, this seems to be a good approach to use the average based on these temperatures, at least for this one. So I think this is there's a lot of information, a lot of understanding here, but also something I want to cement home, hammer home, boom, boom, boom. That specific heat is we treat it like a constant often, but it is related to temperature. So bear that in mind.